All right, so let's go over some questions from exam 3B. Okay, question 1. How many of the 4 compounds above have atoms with tetrahedral electron domain geometry? So tetrahedral electron domain geometry means you have 4 electron domains around them. So if we consider thiophene over here, we have this sulfur atom. Okay, we have two lone pairs on this, meaning we should have a tetrahedral electron domain geometry in thiophene. And also in heptane, we have these carbon atoms here. Remember, these carbons in xanthines are carbon atoms. Okay, and then the common bonding pattern of the carbon is fulfilled by the carbon hydrogen bonds. So you see that we have 4 bonds around the carbon atom, meaning 4 electron domains, meaning a tetrahedral electron domain geometry. And in toluene, we have this N carbon over here with 3 carbon hydrogen bonds, meaning we have a tetrahedral electron domain geometry, because 4 bonding electron domains means 4 electron domains. 4 electron domains means tetrahedral electron domain geometry. And then in pyrrole, we have this nitrogen over here with a lone pair to fulfill the octet. Okay, how do we know there's a lone pair? We have 3 bonds around it, 2 carbon nitrogen bonds, and then 1 nitrogen hydrogen bond. Therefore, 6 electrons to make sure it has an octet. We need to add a lone pair. That's how we know that there should be a lone pair there. And then therefore we have 1, 2, 3, 4 electron domains around it, meaning electron domain geometry is tetrahedral. So all of them, okay, should have atoms with tetrahedral electron domain geometries. Question 2. What is the molecular geometry around sulfur atom of thiophene and the nitrogen atom of pyrrole? Sulfur atom, they're talking about the molecular geometry now. So in sulfur, what we have is a tetrahedral electron domain geometry with the 2 bonding electron domains. Then that bond, so therefore the molecule, the atoms arranged in a bent geometry. Okay, so therefore we have a bent geometry around over here with an angle less than 109.5. Therefore, it should be bent. Therefore, it cannot be option B or D, because we know around sulfur it is bent. And then on nitrogen, we have 4 electron domains. One of them is a lone pair, and the other ones are bonding electron pairs. So they are going to arrange in a trigonal planar trigonal planar molecular geometry. Okay, so it should be something like that. And therefore, the correct answer must be option A over here. Okay, where we have bent around sulfur and trigonal pyramidal around the nitrogen atom. Question 3, estimate the values of the 2 bond angles around S and N atoms. So sulfur, we start the electron domain geometry is tetrahedral, therefore the basic or primitive bond angle is 109.5 degrees. And because we have 2 lone pairs, the bond angle should be pinched a little bit smaller than 109.5 around sulfur. And then when it comes to nitrogen, the same case, right? We have 4 electron domains around it, and therefore the basic bond angle is 109.5. Because the lone pair takes up more space, that bond angle will be pinched. Therefore, the bond angle should be less than 109.5 in both cases. The correct answer is option B. Question 4, identify the atom in the above molecules where we can find valence electrons in the lowest potential energy state. Okay, so remember the potential energy is related to the strength of attractive interactions. In this case, we're talking about attractive interactions between the electrons and the nuclei. And then the most electronegative atom out of all of these should be nitrogen. Therefore, meaning the electrons are more strongly attracted to the nitrogen nucleus compared to other nuclei. Therefore, it should have the lowest potential energy. So, therefore, the correct answer is option C. Question 5, how many of the above molecules are capable of hydrogen bonding interactions? Okay, so the only possibility is spiral over here. Okay, the others are not capable of hydrogen bonding interactions with themselves, or even with others actually, right? Because you don't have, except for pyrrole, none of the others have hydrogen covalently bonded to either nitrogen, oxygen, or fluorine. Okay, therefore there are no hydrogen bonding interactions between the same type of molecule. And also, even if it is with something else, you do not have nitrogen, oxygen, or fluorine in thiophene, heptane, or toluene. Therefore, it's not going to be able to hydrogen bond with something like even water or NH2, anything like that. So it should be just pyrrole, only one of them. Which of the following statements best describe the differences in boiling points between toluene and heptane? So heptane boiling point is 98, while toluene is 111. Okay, so definitely it tells me that overall intermolecular forces are weaker in heptane. So that is correct. Heptane is less polarizable as it has more electrons. No, it doesn't even make sense. Okay, if it has more electrons, it should be more polarizable. So that statement is incorrect without even counting the electrons. But I believe that you can see that you have more electrons in heptane. Now, if we do something to let's try to count that. Let's heptane. Okay, so even if you counted the electrons, we have carbon. See if I can draw. Okay, so we have carbon, 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 and then we should have 3 over here, carbon hydrogens, and a lot more over here. Okay, and then right, so we have 7 carbons, 1, 2, 3, 4, 5, 6, 7, and then we have hydrogens, 14, 16. Let's count 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16 hydrogens. Okay, and in toluene, we have carbons at the bends, and then at the terminal, the end, and then we have carbon hydrogen bonds in these 5 carbons. Okay, so we have 7 carbons again, but we have less hydrogens now, right? We have 1, 2, 3, 4, 5, 6, 7, 8. Only 8 hydrogens. Yeah, so definitely we're going to have less electrons in toluene compared to heptane, right? So therefore, that statement is incorrect. Okay, heptane must be more polarizable because it has more electrons. Anyway, the third option is statement is heptane has has more. I'm sorry, it should be has here. Heptane is more stackable due to its planar structure. Yeah, that is correct. Okay. No, that is incorrect because toluene is more stackable due to its planar structure because toluene has trigonal planar carbon atoms, but heptane does not. Heptane carbon atoms are tetrahedral. They are not planar. Okay, therefore they are not as stackable as toluene. Therefore, that is incorrect as well. Okay, therefore the correct answer is option 1. Okay, so only one. Question 7. Arrange the following species from least to most polarizable. So now it's about the number of electrons. So heptane seems to be having a lot of electrons, but let's count the others as well. So we have carbons over here, meaning there should be carbon hydrogen bonds. Okay, so the formula is C4H4 and S. And then in pyrrole, we have this situation should be C4H5N. Okay, so if you count the electrons, So let's count, why not, right? So each carbon gives us 6 electrons, so 4 times 6 plus 4 times 1 from the 4 hydrogens, and then sulfur, the atomic number is 16, therefore it should bring us 16 electrons. So altogether we have 4, 24, 24, 4, 40, 44 electrons over here. And in heptane, we have 7 times 6 plus 16 times 1. 7 times 6 is 42. 42 plus 16 is 58. 58 electrons. And then toluene, again, 7 times 6 plus 8. 42 plus 8, it should be 50 electrons. Let's write 44 here, 44 electrons here, 50 electrons in toluene. And in pyrrole, we have 4 times 6 plus 5 times 1 plus nitrogen has 7 electrons because atomic number of nitrogen is 7. So if you add them up, it should be 4 times 6, 24, 24, 29, only 36 electrons. It should be least polarizable. Okay, so based on the number of electrons, heptane is the most polarizable. These guys are out. And then it should be toluene, and thiophene and pyrrole should be least polarizable. So therefore, it should be this. Pyrrole. Okay, there are only 3 options here. So pyrrole, thiophene, and heptane. So there's no doubt about that. Okay, so that should be your answer. All right, moving on to question 8. There's evidence for liquid silicate layer atop the Martian core. What is true about the resonance in SiO32 minus silicate ion? All right, the kinetic energy of the system. So we're talking about resonance here. Resonance means extended delocalization of electrons. Whenever the delocalization of electrons happen, the kinetic energy goes down because the electrons slow down, and because electrons has more space to move around now. And then also the potential energy goes down because you have less electron-electron repulsions, for instance. Okay, so let's read these statements. Number one, statement 1: the kinetic energy of the system is increased as electrons have more space to move around. It doesn't increase, it decreases, right? So this is wrong. So they have both kinetic energy and potential energy decrease, not increase. Okay, so this is incorrect. And then it stabilizes silicate and it decreases the total energy of the system. Yeah, that is true, because both potential energy and kinetic energy go down, meaning total energy goes down. When the total energy goes down, it is stabilizing. And option 3, the potential energy of the system is decreased due to decreased electron-electron repulsions. Okay, that is correct as well. The potential energy decreases because there are less electron-electron repulsions. I like it. Okay, so 2 and 3, which is option C, should be the correct answer there. Siloxanes, a mineral found in Martian crust, consists of SiO bonds. Among the following bonds, which ones are most likely less polar than SiO bond? Okay, so first of all, SiO bond. Okay, so if you look at SiO bond, the silicon electronegativity is 1.9, oxygen is 3.5. Okay, so 1.9, 3.5, carbon is 2.5, oxygen is 3.5, oxygen is 3.5, fluorine is 4.0, hydrogen is 2.1, oxygen is 3.5. and nitrogen is 3.0, and fluorine is 4.0. Okay, so if you look at the electronegativity differences, in the first case it is 1.0, and here is just 0.5, here is 1.4, and then here it is 1.0. So now you can check the nitrogen electronegativity just to make sure it is 3, and oxygen is 3.5 still. Okay, so and then for silicate, so SiO bond, the electronegativity difference is 1.6. This difference is 1.6. So SiO bond seems to be the most polar bond based on the electronegativity difference, because we know the bond polarity is proportional to or depends on the electronegativity difference. Okay, greater the electronegativity difference between the two atoms, more polar the bond is. So out of all these bonds, SiO bond is the most polar bond. Therefore, the answer to the question, which ones are most likely less polar than SiO bond? All of them. Therefore, option D must be correct. All right, which of the following substances do you expect to exhibit resonance? Okay, so for this you need to draw the Lewis structures. Okay, so if you look at SCO3, Sc brings 6 electrons, oxygen brings six as well, but you have 3 of them. 3 times 6 is 18, and then the -2 charge gives us 2 electrons. Should be 26 electrons, meaning 13 electron pairs. Okay, so if you draw the Lewis structure of that, we will draw Sc in the middle, even though they have the same common bonding capacity. The Sc is much larger than oxygen, therefore it goes in the middle. And then we have 1, 2, 3 oxygens bound to it. And then I'm going to distribute my 13 electron pairs, starting with the outer atoms. So I have already used 3 in the bonds. 1, 2, 3 is 4, 5, 6, 7, 8, 9, 10, 11, 12, and the 13th one should go on top of selenium or Sc. Okay, so that's it. And then this should be the Lewis structure of SCO32 minus ion. That's it. There are no resonance. Okay, it's because why there's no resonance? All of my atoms have an octet, and there's no reason to delocalize electrons from delocalize no pair electrons between Sc and oxygen, because that's going to break the common bonding pattern, and also the octet not the common bonding pattern, is going to break the octet rule if we do that. Because of that, I'm not going to do that. Okay, so that is that. And then when it comes to SCO2, again, we do the same thing. Sc brings 6 electrons, O2 brings 6, but we have 2 of them. There should be 12. We have 18 electrons in total, meaning 9 electron pairs. Okay, again, Sc in the middle, and there should be 2 oxygens bound to it. I feel like I should have drawn it a little bit above for a reason. Okay, so Sc in the middle, and then we have 2 oxygens bound to it. And then I'm going to distribute my 9 electron pairs starting with oxygen atoms. 1, 2 in the bonds, 4, 5, 6, 7, 8, 9. Okay, so I distributed my that already. Okay, 1, 2, 3, 4, 5, 6, 7, 8. Okay, ninth one should go on Sc like that. Okay, so once I do that, I see that I have octets on my oxygens, but on selenium, I only have 6 electrons around it. Now I have 2 options. Either I can delocalize electrons from here, 1, or from here, 2. I have 2 options. Okay, so if I do 1, then I'm gonna get the double bond on this side, And this should be my Lewis structure. If I do 2, then my double bond would be on the other side. Okay, so I see that I can draw 2 Lewis structures. I mean, it has 2 resonance structures. So therefore we have resonance in SCO2. Okay, so the answer to the question, which of the following substances do you expect to exhibit resonance? Only SCO2, which is option B. All right, question 11, amino acids could have been formed during the Notion Martian, because in Notion Martian, that's an era where you had a lot of meteorite collisions, or asteroid collisions, something like that on Mars. Okay, and then they say that during these collisions, I mean, because of the atoms coming together and because of the heat and everything, there could be a lot of reactions that could give rise to molecules like amino acids, which are kind of building blocks for life. Anyway, so that's a different story. But anyway, it doesn't matter to this question, but they're asking us to identify the functional groups present in the amino acid shown to the right. Okay, so we'll do that. So we have an hydroxyl group, hydroxyl. We have an amine group. We have a carboxyl group. And then we have this phenyl group. So these are the 4 functional groups we find in this molecule. So we know them when we see them. That's the idea of functional groups. So we have amine, hydroxyl, phenyl, amine, carboxyl, phenyl, hydroxyl. So that should be option A. Yeah, there are no aldehydes. This is less. There's no ketone, and there's no aldehyde. Okay. Anyway, yeah. So correct answer is option A. Question 12. Another amino acid is shown below. Which of the indicated interactions can be classified as hydrogen bonding forces? Yeah. So in the hydrogen bonding forces, the 2 requirements are we need hydrogen covalently bonded to nitrogen, oxygen, or fluorine. Okay, because we're talking about water. Water has that requirement already. And the second requirement is that hydrogen must be sandwiched between nitrogen, oxygen, or fluorine. Okay, so we see that not happening in 1, because this is a sulfur, which is not nitrogen, oxygen, or fluorine. Therefore, 1 is out. And then option 2 is fine, because this is hydrogen covalently bonded to oxygen. Okay, and that is sandwiched between another oxygen atom. Therefore, 2 is good. And also option 3, we see hydrogen covalently bonded to this oxygen over here. Okay, is sandwiched between this oxygen and this oxygen. So this is 3. So 2 and 3 only are the correct answers there. All right, moving on. The following peg diagram corresponds to the process of mixing phenol with water with ethanol. Which statement best describes the solubility of phenol in ethanol? All right, so now we discussed this in class as well, right? So if we look at this quadrant, so this quadrant over here is the nice quadrant where you have a lower potential energy, therefore potential energy favors it, and also it has a higher number of configurations, therefore number of configuration favors it. Okay, because both potential energy and number of configurations favor this state, it is always favored no matter what the temperature is. Okay, this is always soluble. Okay, and then also because the mixed state has a lower potential energy, decreasing temperature will increase the solubility. Or in other words, increasing temperature will decrease the solubility, because increasing temperature will start favoring the unmixed state, which has a higher potential energy. So that's the idea. Okay, so the options are phenol is soluble in water, in ethanol at all temperatures. That's true. Okay, this is good. This is good up to this point. Okay, And temperature does not affect the solubility. I think that part I don't agree. Solubility should should change the temperature. Okay, so for that reason, I'm gonna eliminate option A for now. Option B, phenol is soluble in ethanol only at low temperatures. That is not correct. Okay. Phenol is soluble in ethanol at all temperatures, but increasing temperature will decrease the solubility. Yeah, that is perfect. Okay, all temperatures, soluble at all temperatures, correct. An increase in temperature will decrease the solubility is also correct, because increase in temperature will favor the state with higher potential energy, which is the unmixed state. Now it will decrease the solubility slightly. Therefore, option C is correct. Let's read option D for fun. Phenol is insoluble in ethanol. No, that's incorrect. Sure. Okay, so the correct answer is option C. All right, question 14. What types of intermolecular forces exist between CH3F molecules? So remember, CH3F looks something like this, right? This is 3D representation on a 2D plane of CH3F. Anyway, the point is, now this is a polar molecule because we have fluorine. There should be a dipole moment going towards fluorine like this, a dipole moment. Okay, therefore there will be definitely dipole-dipole interactions, and there could be another molecule of CH3F. Okay, so dipole-dipole interactions are there, and then all the molecules have dispersion interactions, because if you have an electron cloud, which all the molecules do, then that electron cloud can be perturbed, meaning polarized, to give temporary partial charges, and then these temporary opposite partial charges can attract each other. Those are called dispersion forces. So dispersion force is also there. There are no hydrogen bonded because you do not have hydrogen covalently bonded to nitrogen, oxygen, or fluorine. Okay, for that reason, there's no hydrogen bonding. So option A is out. Dipole and dispersion only is correct. This is out. This is out as well. Okay, so option B is the correct answer there. All right, question 15. Which of the following images best represents the strongest dipole-dipole interactions between ethanol molecules, or these are ethanol molecules, which was introduced to us in question 13. Now, anyway, dipole-dipole, always the head of one dipole interacts or touches or interacts with the tail of the other one. Okay, and then it cannot be option A. Okay, that looks so weird. And option B looks really good. Okay, option C is incorrect. The reason is the dipole, the heads, the orientation of the arrows look okay. The only problem is the dipole, the direction of the net dipole is incorrect based on what is drawn here. Okay, so the dipole direction, the head of the net dipole moment should be going towards oxygen, because oxygen is partially negative. Okay, for that reason, option C is out. Option D is incorrect because heads are partially negative. They repel each other. There are no dipole, any attractions there. All right, so correct answer is option B. All right, moving on to the last multiple choice question, which is the most likely polymer that would be made by the monomer structure shown to the right. All right, so way to do this is, first you need to draw out the monomer. That's what I would recommend you doing. Okay, so if this monomer, if you draw the Lewis structure, it looks like this. Okay, so goodness. Okay, let's draw it here. Oxygen, carbon, there's a CH3 group, and there's an oxygen over here, and there's hydrogen over here. Now, I prefer to draw it as a line structure because my answers are in line structures. So if I make that a line structure, it's gonna look like, draw it with an angle. because it's easier when I do that. Okay, if I draw the line structure of that, let me draw it like this because it's easier to convert. Here's the double bond. Here's my 1, 2. Let's say this is my third carbon. Okay, so let's say that I drew 1 here, 2 here, and here's my, to the second carbon you have oxygen bound, and to that you have the third carbon bound, and from that we have a methyl group coming out, and here's oxygen. Okay, so this should be my my line structure of the monomer. Okay, and then when this polymerizes, what's going to happen is the double bond disappears. Okay, and it's going to repeat n times, and also to show that it is making bonds with the adjacent repeat units, so adjacent monomers. We're going to draw a bond coming out like that. So it should look like this. Okay, and that is not A because there's an obvious oxygen over there, and that looks like B, and that is, yeah, that's definitely not C, because I don't know what's going on here. All right, that is not what we have in our monomer. And then that is not D because you cannot have the double bond in the because double bond breaks when the monomer polymerizes. For that reason, the correct answer is option B. All right, so with that, let me see. All right, let's move on to not the multiple choice. We just did the multiple choice, the free response part of the exam. Right. FR1, phenol is generally soluble in water. What does it tell us? The number of configurations wise, the mixed state should have a higher number of configurations than the unmixed state, and it's less soluble at at temperatures below 67 degrees Celsius, and soluble at temperatures higher than 67 degrees Celsius, meaning mixed state should be at a higher potential energy, because that means when you increase the temperature, the solubility increases. That's what this second sentence tells us. Okay, the only way this could happen is mixed state is favored at high temperatures. Okay, if the mixed state is favored at high temperatures, the mixed state must have a higher potential energy. Okay, so the potential energy wise, the mixed state should have a higher potential energy than the unmixed state. Okay, now we're going to put this in a peg diagram. If we do that, potential energy and number of configurations are 2 axes. Okay, the mixed state should have a higher potential energy and a higher number of configurations than the unmixed state, so therefore it should look something like this. Okay, so you should get some points for relative placement of the mixed and the unmixed state, and then labeling the axes correctly and so forth. All right, and there are two parts for this question. Which state has strong intermolecular forces? To justify your answer based on the Peg diagram. Okay, so the unmixed state, I'm going to circle unmixed state, has stronger intermolecular forces. And what's the justification? Okay, unmixed state has a lower potential energy. Okay, so let's try the justification like this. The stronger the IMFs, intermolecular forces, the lower the potential energy. Okay, so that's the main thing. Okay, and we see that unmixed state has a lower potential energy. UM has a lower potential energy. Therefore, this is actually repeating, IMFs are stronger. in UM is the unmixed state, which is defined over there. All right, so that's that. Okay, so we get 2 points for circling the unmixed state and then justification, 2 points. Okay, and moving on to question 2, 2 isomers of N-heptane, and I said not shown below, 2 isomers of heptane, N-heptane and isoheptane are shown below. Which substance do you expect to be more volatile? All right, so now, okay, first of all, again, there are 2 parts. Okay, first you need to select which substance you expect to be more volatile, and then you have to justify your answer. 2 things. Okay, so more volatile means you have weaker intermolecular forces. Okay, because if you have weak intermolecular forces, it is easy to go to the gas phase, meaning it is more volatile. So I'm gonna pick isoheptane as my more volatile substance. Okay, why? I'm gonna write the justification like this: isoheptane has weaker IMFs, intermolecular forces. I don't have to write out IMFs and intermolecular forces anymore because IMFs is defined already. Okay, intermolecular forces. That's the justification, but I need to tell why as well. Okay, so that's not going to be enough. Justify considering the types and strength of intermolecular forces. Okay, so what are the types of intermolecular forces we can have? We can only have dispersion forces. Okay, we can write the dispersion forces. If I can undo that, my D. Okay, we can write the dispersion forces are weaker in isoheptane because, okay, we can call it branching, okay, because branching decreases the surface area of contact. Okay, so when you have a lower surface area of contact, right, you're going to have weaker intermolecular forces, because if you do not have, if the molecules cannot come closer to each other, then they cannot have strong interactions. This branching over here, or this thing sticking out from the main molecule over here, act as barriers for the molecules to come closer to each other, and that's why we have the intermolecular forces are weakened in isoheptane compared to heptane, even though they have the same number of atoms. Okay. All right. And then it doesn't have any other intermolecular forces rather than dispersion, because hydrocarbons, the molecule made of only hydrogen and carbon, are considered non-polar for all intents and purposes. All right, moving on to question 3. The structure of furan is shown in the table below. Okay, here we go. Draw all the types of intermolecular forces in a pure sample of furan. All right. So say dispersion forces. Okay, dispersion. To draw dispersion forces, I would draw the molecule first. Okay, and its electron cloud like that, and then I would draw another molecule over here. Okay, I would draw its electron cloud like that, and then I would draw charges randomly, positive, negative, negative, positive, negative, like that. And then I would draw 3 dots between the opposite partial charges of the adjacent molecules to show that they interact with each other. So these are my dispersion forces. And the dipole-dipole forces, okay, again, every time you talk about dipole-dipole, it should be one dipole. Should I like to draw the dipole in red if you don't mind? Okay, here's one dipole. And when it interacts with another dipole, it should be head to tail. Okay, why? Head is partially negative, tail is partially positive. They attract, opposite partial charges attract each other. Okay, so then I would draw the molecule on top of this. So oxygen is the partial negative atom. Therefore, it gets the head of the dipole, and then the tail must be between them, between the 2 carbon atoms or something like that. Okay, and then head is always negative, is oxygen, because it's in this case it's oxygen because it's more electronegative and it has a partial negative charge. And then the molecule behind it should be partially positive. Okay, something like that. So that should be dipole-dipole interactions. Hydrogen bonding, there's no way we can have hydrogen bonding interactions in a pure sample of furan. Okay, so I'm gonna say not available or not present, something like that. Okay, and I need to justify, explain why as well, explain why not, if it's not possible, because I don't have hydrogen. We do not, let's write like this: no hydrogen atoms covalently bonded to nitrogen, oxygen, or fluorine. Okay, if you don't have that, okay, then there's no hydrogen bonding. All right, moving on to question 4. The table below, the table shows the line structures and boiling points of 2 compounds. Explain the relative boiling points of these 2 substances. Hint, make sure to list intermolecular forces of each compound as part of your explanation. Okay, so let's do this. All right, first of all, let me get rid of my arrow over here because it's not needed anymore. All right, pyrrole. Okay, it's a molecule, it's a polar molecule. Okay, and then it also has hydrogen covalently bonded to nitrogen. As a result of that, it's going to have dispersion. I'm going to write dispersion. It's going to have dispersion. It's going to also have dipole-dipole because it's a polar molecule, because nitrogen is more negative than the other atoms in the molecule. As a result of that, nitrogen will have a partial negative charge, other atoms will have a partial positive charge. Then we're going to have dipole-dipole forces. Okay, and also it has hydrogen bonding forces. Okay, why? We have hydrogen covalently bonded to nitrogen, and that can hydrogen bond with the nitrogen of an adjacent pyrrole molecule. On the other hand, furan, okay, it's a polar molecule. Okay, that's true, but it does not. Therefore, it has dispersion and dipole-dipole, but it does not have hydrogen covalently bonded to nitrogen, oxygen, or fluorine. Okay, therefore, there are no hydrogen bonding. So we have dispersion and dipole-dipole. Okay, and furan. That's it. There's no hydrogen bonding. Okay. Now explain the relative boiling points of these 2 substances. Okay. Now the only reason is, all right, the easiest thing to say is Okay, first of all, if it has a higher boiling point, it should have stronger intermolecular forces. Okay, I can say IMFs are stronger in pyrrole. Okay, now that's the first thing, pyrrole, because we know that it has a higher boiling point. Okay, that's number one. Okay, now why this is the case? Because it has hydrogen bonding contribution on top of dispersion and dipole-dipole. Why? Okay, because pyrrole has H bonding forces in addition to dispersion and dipole forces. Okay, so for that reason, you shouldn't have stronger overall intermolecular forces in pyrrole, therefore higher boiling point, melting point, density, viscosity, and all those good stuff. All right, so this should take care of that 8 points then, huh? Okay. Yeah. So I think the main points are you need to list the intermolecular forces. It's asked you to list it. Okay. So I would assume that we're gonna get at least 1 point each for listing this. Okay, maybe I don't write that. Okay, that's 5 points, and then say that's 5 points, and then there are 3 more points, and 1 point for saying intermolecular forces are strong in pyrrole, and then 2 points for saying that because it's because of the hydrogen bonding force contribution on top of dispersion and dipole-dipole. Okay, I think that should take care of that. All right, moving on to FR5, another 8-point question. The structure of water-soluble synthetic polymer is shown to the right. Draw the structure of the monomer, which is great. Okay. Now, here's what you need to know. So we have a carbon over here. Here's 1, here's 2, and that is what is repeated. Okay, over and over. So I would draw those 2 first. Okay, and then here's the 3rd one. Here's the 4th carbon. So I'm going to draw those out first. Okay, so here are the 2 carbon atoms repeated. I draw that first, 1 and 2, and then I have the 4th carbon coming out. The 4th carbon, I have an oxygen bound, and then another oxygen bound, and then OH. Actually, it's an this a carboxyl group, and then to that I have a methyl group attached as well. Okay, that's my 3rd carbon. 3rd, 4th. This is my 2nd. Okay, that's the first thing I do. Okay, I draw out the carbon atoms, and then things bonded to it. Okay, now what's going to happen is when we draw the monomer from the polymer, instead of drawing these 2 bonds, let me use a different color. Instead of drawing these 2 bonds, okay, that is coming out to make bonds with the adjacent monomers, I'm going to draw a double bond between the 1 and 2 carbon. Okay, so that should be my my monomer structure. Okay, you can draw it like this, or you can just make it a bit more beautiful if you want to, like by drawing it out a little bit nicely like this. Okay, and then you don't have to draw numbers anymore. You just need to draw that. That's a line stock. It doesn't specify whether you need to draw a line or do something like that. So drawing that should suffice. All right, that's one. And draw the monomer with one modification. So here's the monomer. Then I need to modify it. Now read the question very carefully. Make one modification to the monomer to make the polymer less water soluble. Okay, so I want to make it less like water, or interactions wise less like water. Okay, that's the idea. So what I can do is I can get rid of the OH group. Okay, I can just say that I can do something like this. So I'm going to draw all this the same. Okay, and then I'm going to even draw this one fine. And then instead of drawing the OH, I'm going to replace that with the CH3 group, which is non-polar. Okay. Now, when I remove that OH group from there, I reduce the dipole moment or the polarity. I reduce its polarity, and also I took away hydrogen bonding sites. Not all of them. Two of the hydrogen bonding sites. Okay. So as a result of that, my polymer is going to become less water soluble now. All right, so that's what I'm going to justify here. Okay, so I'm going to say that replacing the OH group with CH3 group. Okay, group makes it less polar with less H bonding sites. Okay, replace the OH group with CH3 group, makes it less polar with less hydrogen bonding sites. Okay, I think this should takes care of it. Okay, the idea is I make it less like water. I mean, I removed the interactions with water. Okay, I removed some interactions with water. That's what I did. Okay, so it's going to, we can write, if you want to, you can write therefore it interacts less with water. Therefore, it interacts less with water. Okay, so I think that should take care of it. That's it. We're done. Okay. Yeah, I hope you find this useful. I'll see you guys in class. Bye, everybody.